All right. So in the next this video, we will look into the other sliding window protocol. So earlier video, I have shown you one-bit sliding window protocol. The performance of that would be better provided the assumption was that the transmission time required for a frame to arrive at the receiver plus the transmission time for the acknowledgement to come back is negligible. Means the transmission, let me write. The performance of one-bit sliding window protocol will be superior only if, with the assumption that, if we have the assumption that the transmission time and propagation time of the frame and the acknowledgement from the other side is negligible. Other side is negligible. But in reality, this is not so. Like, to give an example, for instance, if you consider this scenario, a very interesting scenario. Okay, in practice, what actually may happen? In practice, the transmission time will not be negligible. To understand that, consider this example. Let's say we have a 50. Let's say, assume we have a 50 kbps. The bandwidth size 50 kbps. Satellite channel is there. We have a satellite channel with a 500 millisecond round trip delay. If frame size, understand this example clearly, if frame size is 1000 bits, 1000 bits is what? 1K, 1 kilobits. Then let us understand the scenario, what is going to happen here. Say, for example, this is machine A, this is machine B. Okay, this round trip propagation time needed for this satellite channel is 500 round trip. Okay, propagation delay. So that means one side it is 250. So how much time does it take using this channel capacity 50 kbps for this machine A to output this frame of size 1 kb onto this? So please understand, 50 kilobits of data can be put in 1 second. So 1 kilobits of data will take how much time? So 1K divided by 50K seconds, is it not? So that is 1 by 5 into 10 power minus 1, which is 0.2 into 10 power minus 1, which is equal to 2 into 10 power minus 2 seconds. This is in seconds, remember, seconds. So this is nothing but 20 into 10 power minus 3 seconds, which is nothing but 20 milliseconds. So propagation time for putting the frame onto the channel is 20 milliseconds. Then after that, it will take 250 milliseconds for arriving at the other side. So total how much? So at what time? Suppose if I start at time 0, then the time at which this will get the frame is 270 milliseconds. You're getting my point? 250 is one-way time, propagation time, plus 20 milliseconds. So 270 it arrives. Assume that the acknowledgement size is negligible. So therefore, with 0 time, it will put the acknowledgement onto it, and with another 50 millisecond, it will. So this is the time taken from here to here. And now for the acknowledgement to start with negligible time of transmission, and it will take 250 another milliseconds. Then the acknowledgement will hit at the sender, at the host A. So total how much time now will the acknowledgement come? Because you stop and wait, sender will send the frame, wait for acknowledgement, right? Stop and wait, 1 bit. So 270 plus 250, which is 520. So this will receive the frame at time 520 millisecond acknowledgement. This is the frame. So frame arrival starts at 0. arrives at the other side at 270. Why 270? 0 plus 20. 20 millisecond for transmission, 250 millisecond for propagation. 20 plus 250, 270. Then it will arrive. The acknowledgement of 0 size arrives at is sent by sender B and arrives at the other end with a propagation delay of 250. So 270 plus 250, 520. So from 0 to 20, it was busy sending the frame. From 20 onwards, it was stuck. It was idle. So what is the percentage idleness? It was idle for, out of 520, at 520 it gave 0 to 20 it was busy, so remaining 500 millisecond it was idle. So percentage idleness of the machine is 500 millisecond divided by 520 milliseconds, right? So if you simplify that, that is 96%. That means the efficiency of the system is nothing but only 100 minus 96%, 4%, which is equal to 4%. Are you getting my point? The efficiency of this protocol is, stop and wait protocol, is only 4%. In other way, you can also calculate like this. Efficiency is equal to 20 millisecond out of 520 it was busy, right? So this goes 1 by 2 to the 4, 2 6 are 12, 1 by 26, which is 4%. 1 by 26 you can check, it is 4%. So that's the drawback of this protocol. There is a drawback of this protocol. So what is the solution for this now? The solution to this is, the solution to this problem of idleness of 96% is that, the solution to this is the sender must not wait for the acknowledgement to arrive. Rather it should continue to transmit the frames, say W frames, W is the number, until the first acknowledgement arrives. Until the first acknowledgement. Why should it wait? See, 500 units it is waiting. Why should? So in that 500 units of time, whatever number of frames it can send, it should continue to send. So within 500, how many frames it can send? Number of frame W that it can send is nothing but 500 divided by time of transmission of one frame 20, which is equal to 25. So it can send 25. It can fill up the pipeline. It can fill up the channel. You look at this. It can fill up this channel. It can fill up this channel with all 20 millisecond duration, right? 25 frames it can frame. 25 frames. So it can fit 25 frames. But what happens? Another frame, the acknowledgement also take 20 milliseconds of time to arrive, right? So it can continuously put 25 frames. It can continuously put 25 frames. 1 second. So it can continuously send 25 frames, and that means that this 25 it can send within this time for which it was blocked. It was blocked for 500, right? 500. So within this 500 it can send 25. Plus it has already sent the first frame, right? It has already sent after sending the first frame, this was the first frame. After sending the first frame, it got blocked for 500. So within this blocking time, it can send 25, this first frame. So total, the maximum size of W will 26, right? This is generally this number, the number of frames that it can send before getting blocked. The number of frames that it can put into the pipeline before it can get blocked, for example, is before the first acknowledgement comes is 26. Blocking time, number of frames that can fit in the channel, 25, plus first the time plus one of the frame can also be sent in the beginning. So 25 plus 1 it become 26. So this is the maximum number of frames that it can fill in the pipeline rather than getting blocked. This is generally called bandwidth delay product. What is it called? This is called bandwidth delay product. Bandwidth delay product. We generally write in short as BW or BD. Okay. is called BD, bandwidth delay product. So in our example, the value of the bandwidth delay product is 26. I hope you understood how it is 26 frames. Okay. So how I can give you a simple formula for bandwidth delay product as follows. So I assume some framework here. Let us imagine the protocol support or the system support a channel capacity denoted by, let us say, C, kilobits per second, and let us say the frame size is f bits, and round trip delay is, let us say, d milliseconds. Then the bandwidth delay product BD is given by the formula channel capacity multiplied by one trip time, not round trip, d by 2, divided by the frame size. This will be the formula for bandwidth delay product. Okay. Then the value, what is W? Maximum number of frame that can fit in the pipeline. in the pipeline, I mean, this is host A, this is host B, this is channel capacity. So before I get the acknowledgement, the maximum number of frame that I can fit is W, which is given by 2 into BD, bandwidth delay product, plus 1. 2 into, like in for previous problem, if you take the values, I will draw the line here and show you. Okay. Say for example, of the previous data set, if you take the value of C was 50 kbps, I'm showing you how the computation goes on. Okay. And the value of F is 1 kilobits. The delay time is propagation delay time. Okay, so the delay time was in milliseconds. So therefore, what was the delay time? Total delay time was 500 milliseconds. Round trip time. Propagation round trip delay is D. So how do we compute the bandwidth delay product? Please see. So bandwidth delay product is nothing but channel capacity 50 into D by 2, which is nothing but 250, right? But here you have to be careful. This is in milliseconds, this is in seconds. So you have to convert that into seconds. So 250 milliseconds is equal to how many seconds? 0.25. So I'll write 0.25. All right. Converting into uniform factors. It is in second. This cannot be in milliseconds. So convert it into second. 0.25 seconds. This divided by frame size. What is frame size? 1 kb. Because this is also in K, this will also be K. So 1K, this is also in K. So K cancels. So what is this value? So 5 into 2.5. Is it not? So which is equal to 25, right? 12.5. So this value, bandwidth delay product, is 12.5. So if I multiply 2 into 12.5 plus 1 is equal to 25 plus 1 is equal to 26. That's it. I shown earlier in a theoretical calculation, and now I'm showing practically by means of the formula. So this is the maximum number of frame that can fit in the channel before I get the acknowledgement. This is the maximum, right? So based on this, so this technique of continuously sending the frames without getting blocked is generally called pipelining. So let me write the definition for you. So what is pipelining? Pipelining is a technique of keeping multiple frames in the flight is called pipelining. Like it should not get blocked. Rather than that, it should continuously keep on sending the frames. That is called pipelining. So the remaining two protocols, go back in and selective repeat, is based on this concept of pipelining. Mean the window sizes are more than one, right? So what happens in go back in? In go back in, I will write in properly. In go back n, we write in short as GBN, go back n. The receiver window is always 1, and sender window can be W. What is W? I have already shown you earlier, right? So the point is receiver will discard all out of order frames because its window size is only 1. So if it is 0, it can accept only 0, it cannot accept this, and therefore it will forces the sender to discard, forces the sender to retransmit, forces the sender to go back n frame, the nth frame or the corresponding nth frame which was in a transmission, go back to n frame which is in error, for retransmission. Okay. So therefore, what is the drawback of this? The drawback of this forcing retransmission is, therefore, this will lead to wastage of bandwidth. I will show you diagrammatically how this works and then how does it lead to wastage of bandwidth. But the point is, before we continue, what can be the actual value of W? Right? Or I would say receiver window size. I would rather say receiver window size. Actual value of receiver window size, RW. What is RW? Receiver window size. Like for example, imagine n is number of bits in sequence number, and W is actually the maximum number of frames that can fit in the pipeline. We have already calculated this. We have already calculated using bandwidth delay product, BD, bandwidth delay product. Okay. So the window size, sender window size will always be equal to, that means this is the maximum window size. Maximum sender window size is always equal to minimum of see, number of bits in sequence number is, so total number I can have is 2 power n or W, minimum of this. Like what I'm trying to say, please understand. Suppose for example I am using 3-bit sequence number, then the number of unique sequence numbers I can have are 8, or I can have 8. And then suppose if I say the value of W is 26 like earlier occasion, but I can't fit 26 because in one window I cannot have unique 26 numbers. I can have only 0 to 7 sequence numbers. So it has to be minimum of this. Suppose if I take 10-bit sequence number, then how many I can have? I can have 1024 sequence. But the maximum that I can fit in the channel is 26. I have to take minimum of this. So whichever is minimum of these two, that can be taken as the maximum size of the sender window size. Anyway, receiver window size is how much? Receiver window size in go back n is always 1. So sender side, it can be this. It cannot be. Sender window size is minimum of these two. So now based on this, let us try to understand how it works. I will show you diagrammatically in this presentation. Okay. So please see the presentation. So larger windows enable pipelining for efficient link usage. Stop and wait will have window size only one, which is inefficient. We have already calculated that. So the best window size depend on the bandwidth delay product I already calculated, and the maximum value of W is 2BD plus 1 to ensure high link utilization. So pipelining leads to different choices for errors and buffering. Okay. So what happens here? Please see how go back and protocol works. Receiver only accepts or acknowledgement frame that arrive in order because its window size is only one, and it is compelled to discard frame that follow in order, not in order. Sender times out and resends all outstanding frames that it is supposed to. Look at this. So the sender is receiver. The sender and receiver. So whatever be the size of the sender here, let us not worry about it. But receiver window size. So let me mark it for you. Let it mark it for you. Please follow me. This sender, this receiver. So sender first sends 0, then 1, then 2. So acknowledgement is also sent by receiver 0. So it advanced to 1, accepted, fine. But 2 is in error. Packet or frame 2 is in error. Then sender, because it has larger window, so it keeps on sending the other frames 3, 4, 5, 6, 7, 8 like that. It has continuously sent up to 8. It has continuously sent up to 8. But what happens here? All these are discarded. These are drawback of go back in. It is forcing to go back to 2. That is what it says you keep on sending from 2 because I have not received this. So here frame number 2 got timeout. So sender again retransmit 2, then 3, go back to 2, go back in and retransmit 2, then 3, then 4, then 5, then 6. So these frames were unnecessarily sent again because they were sent already earlier, but now they are retransmitted. These are drawback of go back in. These are retransmitted frames. And it sent acknowledgement 2, 3, 4, 5, 6, 7. Why this is happening? Because of only problem that receiver has window size of only 1. I don't have provision. I don't have buffer for accepting 3, 4, 5, 6, 7, even though 2 was in error. So if I have additional buffers present at the receiver side, then that protocol is called selective repeat. But the question is, what can be the maximum size of the sender window? What can be the maximum size of sender window in go back? And to illustrate that, I give this example. Kindly understand what this scenario says. It's a very beautiful example taken from some source. Okay. Size of the sender window must be less than 2 power m, where what is m? What is m? M is the number of bits in the sequence number. Size of the receiver anyway is all. So if m is equal to 2, please observe. So if m is equal to 2, that is the number of bits in sequence number. Let me write. If m, what is m? M, for your convenience I am writing, m is number of bits of sequence number. So if I use 2-bit sequence number, then I said earlier maximum I can have 4, but it say that you cannot have maximum 4, you have to have 1 less. Why? To illustrate why it should be less by 1, we will take this scenario. So first compare this scenario where I am taking window size, actually would have been maximum 4, but I am taking 3. So what will happen if I take 4? So what if I take m equal to 2 as shown? The number of sequence numbers are 4, which are 0, 1, 2, 3. So sender can have maximum window size of 0, 1, 2, 3. So if it takes 0, 1, 2, 3, then what problem am I going to have? Please observe. So sender send frame 0, but acknowledgement of 0, which is successfully received, is lost. Acknowledgement is lost. These are lost. These loss. But what happens since acknowledgement, because its window is 1, so it sent frame 1. Frame 1 is accepted, acknowledgement lost. Frame 2, it advanced the window to 2 because receiver window size, remember receiver window size is 1. Sender window size here is 4. 0, 1, 2, 3. So all acknowledgements are lost. So what is going to happen? Please observe. So acknowledgement 1 is lost. It slide the window to 2 because it has already sent the acknowledgement for 1. So it slide the window to 2. So it sends 2, accepted, advance the window to 3. So send 3. 3 is also lost. So here what happens? All acknowledgements are lost. 0, 1, 2, 3. So it has accepted 3, sent the acknowledgement, unaware that it is lost, so it will advance the window to 0. So please remember, all acknowledgements of 0, 1, 2, 3 which have been successfully accepted and forwarded to network layer are lost. are lost. So what happens now? Because sender has not received any acknowledgement, so the first frame 0, go back and frame 0 times out. Now frame 0, when it times out, it will retransmit the old frame. But because it is following in the current window receiver is expecting is 0. Current expectation of receiver is 0, which is a new frame. 0 is already accepted, right? 0 is already accepted, but the acknowledgement of that is lost. So I'm showing that now when it has slided from 3 to 0, it is expecting the new frame 0, but old frame 0 comes, and erroneously that is accepted. Erroneously that is accepted by receiver. Why? Because it has lost all the acknowledgements. So this is a problem. So receiver here think that this is a new frame, but actually this is the old frame, and protocol fails. So therefore, if I use receiver window size of sender window size of 2 power n, protocol fails. Protocol fails. So that's why if I take a sender window size of 2 power m minus 1, 4 minus 1 is equal to 3. Look at this 0, 1, 2, 3. Either the window size is only 3, 0, 1, 2. Same scenario if you observe, now it won't fail. Same scenario if you observe, it won't fail. So what happens here? So first it's 0. 0 is lost. Advance the window to 1. It send frame 1, accept and acknowledgement lost. Send frame 2, accept, acknowledgement lost. Okay. Now after 2, it advanced 3. But now, unlike earlier occasion, now it times out and retransmits 0. But 0 is not the expectation. It is expecting 3. So therefore 0 will be discarded. Correctly 0 is discarded. Why? It is expecting 3. It is sending 0. So therefore that will be lost. That will be discarded. So now the protocol is working correctly. So that's why please remember in go back and automatic repeat request protocol, go back and protocol, GBN protocol, the maximum window size with respect to sequence number will be 2 power m minus 1 maximum. This is the maximum with respect to sequence numbers. And finally, as per my presentation, I told minimum of either this value or the pipelining window size, right? So that is the go back end. So next video will take up selective repeat.